Hey guys, it's Visto. We are going to kind of continue our conversation around 3.1, but how, excuse me, how we're going to do is we're going to switch to talking about what are called logistic functions. So if you were to look in the book, which we haven't done yet this year, 3.1 is all about exponential and logistic functions. And logistic functions are pretty cool because they're like exponential functions, but they live inside other rational functions. And what makes them so cool is the applications that exist for them. So when we talk about what are some key characteristics of logistic functions, we're actually going to be talking about characteristics. There we go. We're going to be talking about we're talking about things that actually apply to biology or epidemiology or even just in general, maybe even some sociology stuff, just looking at populations, right? And for us, we are going to be looking mostly at logistic growth. And logistic growth, we can model it one of two ways. So the first way is like this, as this fraction with c on top, and then 1 plus a b to the x, which we looked at yesterday. So that's kind of sweet. Excuse me. Now, the other way to look at this is using a base of e, because then we'd be talking about continuous logistical growth. And when we write it like that, we have C still on top, and C actually plays a pretty important role, and we'll talk about that here as we dig into these a little bit. 1 plus A e to the negative kx. Right, now most of the time you're going to be given all this information, so I wouldn't stress too much about wait, Vista, what's k? How do I know how to find k? We're going to be dealing with equations where all that information is given to us from the get-go. So we talked about how this is used a lot in biology and whatnot. We, if you think about, let's just even talk about people on Earth. Eventually, that population is growing exponentially, right? It's kind of been exploding, at least in my lifetime and probably in your lifetime too. But the Earth has what's called a carrying capacity. We can only hold so many people on the Earth. And so in that case, what we think about is this idea of, okay, there's a max population we can have. And logistic functions model that because C is the limit to our growth. And the reason, or what you may have heard it called maybe in a biology class or something like that, is the carrying capacity or ecology. I feel like Battern would love this. So carrying capacity. Now, when x is 0, that's the initial, right? That's our y-intercept of a graph or of our equation. But in terms of this application sense, that's reflected in our what's called our initial value, right? In other words, where does our population start out at? Okay. Just a quick example. And then what I really want to talk about is some word problems, because that's what your assignment is in Moodle today. But for our example, we're going to have f of x. And I'm going to put 9 in the top over 1 plus 2 to the 0.6 x. So this logistic function right here, let's just graph it. So there's graph 1, 2, 3, 4, 5, 6, 7, 8, 9. That's fine. It'll go way up high, and that's okay. I need it to go way up high, and I'll show you why here shortly. This first of all, this logistic function, we have a carrying capacity, our C. C equals 9, right? That means that that's the most our population can hold, and it actually tells us we have a horizontal asymptote, at y equals 9. So I'm going to draw that in. Because of the way logistic functions work and how they're used to model populations, we also have horizontal asymptote at y equals 0. So we're going to recognize those two horizontal asymptotes. The next piece of the puzzle is what's our initial value? So when x is 0, we can figure out our y-intercept of our graph. So I'm going to go 9 over 1 plus 2.6 to the 0. So 9 over 1 plus 2, but 0.6 anything to the 0 is just 1, which is 9 over 3, which means our y-intercept is at 3. So our initial value, the initial population, that's only at 2, so that's terrible counting, Vistal. Let's try that again, is at 3. And that means our graph will come down here from 0. It starts at 3, or it has a y-intercept of 3. Then eventually it'll reach this carrying capacity of 9. So, what does this actually look like? Well, let's look at a word problem. So, I'm going to talk about this word problem, but I'm not expecting you to write this down. Maybe just listen, take it all in, and kind of hear the key pieces, because there'd be a lot for you to write down. But in this word problem, a certain population of polar bears, B, population B, for bears, we use this logistic growth model. And then it does tell us that T is the number of years since 1900. So that's probably an important part. Evaluate P of 0, right? So that just means I want to plug in 55.1, 1 plus 9.6 e to the negative 0.2515 times 0. Anything to the 0 is just 1. So 1 plus, 1 plus 0.96, right? Because all of this, because it's being raised to this 0 right there, that just equals 1. And if I actually go to my calculator and do this, and I make sure that I do it dividing by 10.6, right? 1 plus 0.96. Gives me about 5.198, so 5.2 I'm going to round it to. Feels weird to have 0.2 of a bear, but we'll roll with it for now. On our graph here, that would be this point right here. That would be B0. That means about 5 bears were in this population of polar bears. Now it says use the equation to give a population beginning of the year 2015. Well, if 0 was 1900, 115 will be for 2015. So we just got to be careful of that real quick. So here we go. We got 55.1. 1 plus 9.6 e to the negative 0.02515, 115. Now, if I'm going to do that in my calculator, I'm going to do it in chunks. I'm going to do 9.6 e raised to the, raised to the negative 0.02515 times 115, right? So I get, if you're doing that with me, if you punch that into your calculator, you know what? I forgot I'm recording my whole screen. Let's calculator. Where was I? So I had 9.6 e. There's that e choice. Raised to the, this calculator's crap. I just want a parenthesis. Forget it. I'm not going to do it along with you, but I will tell you the numbers I get as I go. So the so we can figure it out all together. So the so far we've done just this part right here. And that was about 0.5323. I'm going to add a 1 to that. Now I'm going to get 1.532333. Then I'm going to take 55.1. So let's see. So I'm going to write that down just so I don't lose track. I'm going to get about 35.95, so I'm going to say about 36 bears. So if I look on the graph, if I want to know about 2015, we said that would be about right here. And I feel pretty good saying, yeah, it's about 36 bears. What's the maximum number? Well, the cool thing about maximum, it's just your carrying capacity. 55.1. And then when will it be about 38? About 38 happens right here. It looks like that's maybe 120. So we're going to say when t equals 120, which really means 2020, because it's 120 years after 1900. So I'm going to stop here. I'm going to say, you got this. You can do this. I believe in you. There's a Moodle assignment that has some of these word problems in it. You can do it. I'll make sure it's open and that it tells you your answer right away so you can get it all figured out. But in the meantime, make the magic happen. Ready, set, go.